Good morning, everyone. Welcome. Now, let me ask you a very honest question. Have you ever looked at an engineering drawing and wondered who on earth decided this thing makes sense? Very interesting. You see circles, there are no circles, lines that don't connect, and somehow someone expects you to imagine a full 3D object from just that. Well, don't worry, you're not alone. So today we will fix that. So welcome to this session of orthographic projection, one of the most important and misunderstood topics in engineering drawing. Now, whether you are in mechanical, biomedical, electrical, civil, aerospace, name all those disciplines, or even just starting on technical drawing, or let me call it engineer drawing and design, this topic is your gateway to skill. Because let me tell you something very important. Well, one, every machine ever built, every structure ever constructed began just as an orthographic drawing. Think of this way. Imagine I place a cup in front of you, right here. From where you're seated, you see one view, hypothetically, yes? Now, if you move to the top, you see another view, okay? I'm assuming you're from the top right now, okay? I'm placing it, good. Now, if you move again to the side, you see another view. Here it is. The object has not changed, only your perspective has changed. The line of sight is the foundation of orthographic projection. Now, the problem begins when engineers decide, let's not show just one view. No, let's show three views at the same time. The front, as it was, the top, and the side. So if I'm placing it this way, definitely you're not able to see the top, okay? But if I incline it at an angle as such, I've just inclined it, you can see maybe the side where I'm holding it, and probably partially the top, which is now almost like oval in shape. But when you were on top of it, you were just able to see a complete circle. But when I've inclined it at an angle, if you're able to see a complete circle, then you'll not be able to view all the other parts, the three parts. And then they say, if we combine this, the front, the top, and also the side view, and we start to imagine the object. That's why most students say, sir, respectively, no. But today, we make it simple, very simple. So by the end of the lecture, you'll understand what orthographic projection really is. And remember, although we've applied it in previously in our projection, especially in parabolas and hyperbolas when we are drawing them. So it means right angle at 90 degrees. Okay, I'll explain that later, but at the end of this lecture, again, you'll be able to clearly distinguish between the front view, top, side view, and other terminology that are used. Okay, you'll be able to learn on how to translate a 3D object like this one into 2D drawings. Okay, and avoid the common mistake that causes marks even when you're doing exam. And most importantly, start thinking like an engineer. Okay, and a professional to be. Now, here's how we will approach this problem altogether. We'll not just define things. We will visualize, break down step by step, and connect everything to real engineering practice. From physical class, students you draft this manually. But for my virtual audience, we will also use 3D tools like Inventor today. You'll be able to see what is happening. Because engineering drawing is not about memorizing, it's about seeing what others cannot see. Now let me say this clearly. If you master orthographic projection, you unlock the ability to communicate ideas without speaking. That means you can design, you can build, you can construct machines, and you can solve real world problems. That's the power you are stepping into today. So before we begin, drop in your chat, as usual, where you are joining from. You're my students, you know what the drill, your registration number, which is your course or your field, and let's make this interactive. And if you're watching, this is a replay. Pause, grab your notebook, and follow along with us. So, all right, let's begin with the most fundamental question. What is orthographic projection and why do we need it? Now, pay attention here. This is where everything starts to make sense, okay? Thank you. Beautiful orthographic projection. Mm-hmm. As I said earlier that before, although it basically means perpendicular, and when perpendicular means meeting a right angle at a right angle, that's 90 degrees. So, as I just said there before, the system, this basically a system of drawing views of an object by projecting points perpendicularly, which means the line of sight has to be perpendicular to the view. I mean, a specific, let me say, view, let me say a front view or just a side view or just a plan, which is also the top view. So we are likely in this case to be drawing or just projecting multiviews, whereby two-dimensional views of an object are projected upon two or more planes. In that case, using what you call these techniques of orthographic projection. Now, let me use this to illustrate our discussion. Okay, one moment. Well, I have I have displayed for you in my presentation basically 3D views. Now, pay attention. When I introduce what you call Inventor, I use what you call a plane. Planes are very important for you to be able to visualize. And imagine, like now where you're seated, I also assume it's like a box, but now it's transparent, more of a glass. Okay, it will have four planes. Okay, the top, the sides, and also the front and the rear. The top and the bottom would be just referencing as what we call the horizontal plane. Okay, in either the side view, like this book, I'll just say, I assume it's a box. Okay, the top, the bottom, the side, and also the front, and also the rear part. Now, assume it's like a glass, and you are holding something like, for example, an object, okay, and you're lighting, let me use a torch. What you see is a shade that is being reflected in the rear, and that shade is projected onto the wall. Okay, now we'll start by using what you call planes. Here today, I have already demonstrated by drawing a 3D object in form of a block, as you can see here. Okay, and I have used what you call a plane from the front side, where I've just taken one side as a front, In the line of sight, I've used these arrows point at corners to demonstrate the projection. Okay, as you can see, the hidden lines have just been drawn to illustrate the points which are directly visible and that can be projected. So, in this case, lines of sight are perpendicular to the plane of projection, as you can see in the arrows on the diagram B. In this case, the depth is negligible. Okay, we have sized it so that at least you're able to separate what you're able to view from the actual 3D, the isometric drawing. Beautiful. Now, let me move further. Uh, before let me just go back again. Before we proceed, you are able to say that the way I have positioned it, you're able to see at least three multi-views, which is now from the direction of the arrow, we have taken it as what we call the front view, and where we have labeled as the depth, we would use it as the side view from that direction in the plan where you're able to see a circle from the top. Okay, now let's move a bit further. What do you see? These are what you call multi-views. Multi-views is a combination of three sides, okay? They may be not necessarily three sides, but they can be even more or less, depending on the object itself. And from that perspective, you are saying, here is my top view. If I say it again, when I was using an illustration of a crab, it's your perspective that changed. Now, assuming you're from the top, what you'll be able to see, you'll be able to see such a kind of what? View. If you're from the front, where we are just showing some arrow side, you're able to see the front view. And from the right side, also you're able to see the other view. These all combined, or if you're given these three views, you're able to project or just to draw an isometric drawing from the orthographic views. Remember that it's vice versa. You can draw an isometric drawing from orthographic views, but also you can draw orthographic views from an isometric drawing. Now, these are three views. Later, we'll just talk about what you call first angle projection and third angle projection, whereby how do you position the views? Because we have the front view, the right side view, and also the top view. Why can't you just maybe probably, why are they drawn the way they are drawn? I think the top is where it is on top of the front view, and also the side view or the right view is on the side of the front view. Okay, now I'll explain to you one later. Let's proceed. Yeah, just said again, we want to use an example of a box, a glass box, a model. Now, the purpose of this is to give you what we call the ability to visualize. Visualization is key, especially in engineering drawing. Upon the completion of this lecture, you just realize that you no longer need a lot of struggle just to comprehend or to interpret, simply because you'll be visualizing, not memorizing. Okay. Now, what if you place this object in a glass box, so that the side of the glass of the box is parallel to the major surface of the object? Okay. Now, pieces of the glass box serve as planes. It can be a profile plane of the projection, or profile planes of the projection, or the side view, or the left side, or the right side. Exactly. Now, when you cut the glass box along the edges and fold to obtain the multi-views, basically, that's the model, or that's the concept of using just a glass box to illustrate the 3D views, as well as be able to convert the 3D views of the 3D isometric drawing into 2D views of what we call orthographic drawing. Now, I've talked about third angle projection and also first angle projection. You want to understand one thing. Mostly, third angle projection is used in the US. We will talk about we talked initially about the ISO, the standards, okay, and conventions. So in engineering drawing, but for also mostly ISO standard or international standard, mostly we use they use first angle projection. And the difference between is that the top view is directly above the front view in third angle projection. Okay, I repeat again, the top view is directly above what? The front view. Okay, and the right side view to the right side of the front view. Okay, now that one will depend on where you're viewing it from. And I'll repeat this one again. Depending on the point of view, the right side view or the left side view will be dependent on the point of view. And I'll explain it later when I'm using the Inventor in order to illustrate. For example, if you're viewing it, you ask that now, for example, in this box, which is with us here, you ask that you're viewing it from the right side, drew this, the front view. That means the front view is going to be drawn on the left, or the side view is going to be drawn on this right side of the front view. I repeat again. If you ask, in this case, for example, viewing this box from the right side, okay, do the view from this, let me say from the right side, do the side view. So the side view is going to be projected on the left side, okay, or if it in this glass box is going to be projected on the rear side, okay, and therefore that left, the right, the right side, okay, the side view is going to be drawn on the left side of the front view, and vice versa. But the plan is from the top, which is the front view, the top view, and that's it, is projected on the horizontal view. Okay, now I will demonstrate that later for your understanding so that you don't get too confused any of those. Further, I talked about the third angle projection, and now I'll demonstrate that one using the same box again. Pay attention to the glass box. I'm gonna move back a bit for your information. Now, take your moment. If you're quick, you can always use a few of your draft skills to sketch quickly. But in this case, just pay attention on the plan, the top view, on the side view, or the front view, and the side view. Later, I'll explain to you why or how do you get to choose. For example, if you're not given specifically told that use this as the front view or the side view, how do you get to? What are the considerations you have to decide on making what we call selecting the front view? Okay, one I'll let you know. Now let's move to the orthographic views based on the glass box that I have used there before. Here we go. Now, what are you able to see in this case? Literally, I can just say you're able to see three views, multi-views from the box, okay? Now, the front, the plan or the top view is on top of the single view that is up is what we call the plan. And on beneath it is what we call the front view. And on the right side of the front view is what we call as the side view. And now in this case is the right side view, okay? Now, how is it drawn and why is it where it is? Okay, this is angle projection. What you're able to see is that the plan is on top of the front view, whereas the side view is on the right. Now the right side view is drawn on the right side of the front view. If it were first angle projection, the front view and the side view will remain the same. Only the interchanging of the top view will be below the front view. I'll sketch that one later for your understanding. Okay, I can as well use a different software to illustrate that one. But for now, let me just proceed. I'll do the demonstration later. Beautiful. Now, here's some of the very main questions that we do ask ourselves. What are the planes? What are the terminologies that are being used usually? Okay. Now, the planes, which are known as sometimes the principal projection planes, are what we call, or already what we just mentioned about the front view. Okay, they can be noted by different letters, or sometimes depending on who in who is sketching what. So we will always have what we call the front view, the top view, and the right side or the left side view, etc. Okay, and do not forget that these planes I have what we call their respective what planes. For example, if you have the top view, there's also what we call the bottom view. Okay, which is not if in 3D you just isometric, you just rotate it or twist the box in order at 45 degrees not to be able to view the 3D views while you are able to see the bottom view and also the other side, the front view and also the side view, etc. Which if it was a cube, it would be the same like the top. Okay. Now that's not the most important thing, but let's move forward as we get to comprehend what I want to drive home. Beautiful. Now, when we get to draw projections or we project, be it lines or points or planes from 3D to 2D, it's very important. It's of utmost important to understand and define what you call the dimensions, especially the height, the width, and also the depth. Okay? It's also of utmost importance to be able to align the views in their corresponding dimensions. It's of utmost importance also to pay attention to hidden features and edges by the use of the right or the right water lines. In this case, I talked about in our last discussion, the precedence of lines. In this case, when you're showing hidden features, they are what you use what you call hidden lines to demonstrate that the hidden features they are not visible directly at the point at which you are viewing it. And in that case, I can just use a quick illustration of what we just had. This kind of what we had a 3D yes just view it. Now, as you can see from the front view, from the direction of the arrows, you are not able to see the hole that is penetrating from the top on the right side through this to the bottom of the block. But you're only able to view it or see that there's a hole through it if you're viewing from the top. Okay? Repeat again. So in the front view, you can only communicate to whoever is going to project it or just going to design that or just going to manufacture that oh, there is a hidden feature here. In this case, it's a hole maybe of this length, because when you show dimensions, they communicate exactly that the depth of this hole is approximately, let me say, 10 millimeters deep or through it's through or just to a given length. Okay, now let me proceed again to another illustration to enable us understand what we need to visualize today. Mostly, it becomes a challenge, especially for beginners when you are drawing multi-views. I repeat again, it's always a challenge when you're drawing multi-views. And today, I just want to tell you on the very basic principle of just drawing orthographic views. Start with what we call the front view. Upon completion of the front view, you can draw the plan, which is the top view. Okay? And pay attention to this, that the end product both the plan, the top view, and the front view is what we call the side view. And in this case, I have used what we call a three-space dimensions to illustrate this. Okay. In this case, it's still in third angle projection where we have the front view, the lower left corner, right lower corner is the front view, and on top of the front view is what you call the top of the plan. Now, some of these edges are symmetric about a given point, and they coincide with one another. And now, upon completion, the side view is just a projection of the same lines extended. When we extend, we convert the same length from the plans also downwards on what we call depth Z, converted at 45 degrees, converted orthographically, perpendicularly 90 degrees downwards, we get the depth Z. Okay, in that equally the same length that has been horizontally translated, whereas the front view retains its position but only projects the specific details of the front view, and that's how you end up obtaining the side view. So the side view is just a projection of lines to coincide with one another from the plan and also from the front view to get this. We'll do it in our practical lessons. Okay. Allow me to proceed. Now, it's of utmost importance also to be able to understand that while you are just drawing these views, you just don't throw them here and there. Okay? The views have to be aligned. Okay? Now, for example, check on where I have labeled as the vertical parallel projectors between the front view and also the top view. Okay? The vertical parallel projectors, the hidden lines. Okay. Now, look here. Check on what you call the horizontal parallel projectors. Okay, that length is the length the same as the vertical parallel projector length? If you see by visual, you can tell that the length is not the same. Hence, the right side view is almost closer to the front view, whereas the top view is at a point distance almost twice the distance of the right side view from the front view. What does that tell you? Alignment is very important. Okay? Yes, it may have been drawn perfectly. Okay? But yet, the translation or projection of the side view is, or the front view to the side view is very, very important. I go back again to this one. Now, check again on or just have a look on what I'm just talking about. The depth Z from the front and the top view. Okay? When it's being converted, you realize that it's inclined at 45 degrees. In this case, you can use your set squares of 45 degrees, you convert it and project it at a point distance of the same down up to where the lines coincide with each other. Pay attention. If you are doing the actual projection drawing, in most cases you realize that you do not need to measure the side view. The side view is automatically obtained from both of the views, the front view and the front view, and also the plan of the top view. By projecting the lines which coincide with each other, you're able to trace the length, etc. And you do not need to measure, as applies to the front when starting to do the front view of the plan. Okay, that one will be explained practically in our next lesson. and or by the end of our lesson today. Well, now I want to talk about what are some of the very basic things that you've got to consider when selecting a front view. Selecting a front view, you've got to ensure that first of all, it provides the best shape description of the most characteristics of the contours are visible in the front view. So most of the time when we are select or choosing a front view of orthographic of an isometric drawing to draw orthographic views, we have to make sure that we are selecting in most cases either the view that has the most or which is more descriptive or has most characteristics of contours. It means all the edges where you're able to see this and that and that. It communicates each other a lot of features which are visible if you're viewing from that position. Now, the other view will be then taken as what we call the side view. Okay, pay attention. Repeat again. Apart from being descriptive or more characteristics, just to also have what we call the list of hidden features. The list of hidden features. Now, let's proceed to the next slide. Well, here is a very good example of a mechanical part that has been drawn in 3D and has been projected using projected using the profiles or for our understanding and illustration. Now, based on the view that you are able to see here, I want to illustrate what I've just explained there before about selecting the front view. In the box, you've seen I've labeled the front view, the right side view, and also the front view. Suppose I have taken the right side view as a front view, in this case. Okay, what would you be able to see, or what would be able to? There are quite a number of. Okay, you will only in front of you just be able to see the only one side. Okay, as is. For example, the holes, the two holes which are visible from the plan, cannot be communicated with the two because they coincide with each other in the front view. Therefore, the hidden lines are just one. But unlike when you just go on the right choice that we've taken here at the front view, it has the longest dimension, okay, of the depth. In the hidden lines features of both holes are visible in the front view. Therefore, easily someone will tell that voila, there is a hole, there is a hidden feature on this side or on this side of the block, and I need to move myself in order to be able to view it. And then if you just go to the top, you'll be able to they were really they were holes. But from the front view, you'll be able to see the through hole that is from the front view. And now that one is very well communicated from the side view, the hidden lines. That one also will discuss how those are obtained. Now, this is a very good example of how you are supposed to always consider a front view from a side view, because we always start drawing from the front view in orthographic views when we are translating from 3D to the isometric to orthographic views. Now, let's go to our first demonstration illustration that I used. It is very important for us, and I would like you to really pay attention to this. I used it again in the other time I did using Inventor, the 3D view, and the object I want to illustrate using a glass box. And now in this case, it has been suspended within or in a glass box. And you're able to see all the 6 principles. I talked about the principles as the views, okay, or profiles, the plan, the bottom, the side, in the rear, the front, and also the other profile plane. Okay, those are the principles. Now we are taking this case the image on the left side is just basically like you as a person in your line of sight. You're viewing that block in front of you perpendicular. The line of sight or your eyes are perpendicular to the specific side of the view. Okay, and we've taken that on as the front view. The profile plane is either on the right side when you are specifically viewing it right, or the rear side can be termed or just be used as what you call the profile plane, which is now the side where you've drawn the side view, or the rear side view, which is reflected. Again, I say reflected. As you can see, there's a reflection of the same view darkened in gray in the rear side. Okay. Also from the front view, if you're viewing the view that is in, let me say, not shaded in white, but if you see in the rear, which is shaded in gray, is the same image that has been what reflected on the rear profile, or just a rear water view. Okay, let me call it just the rear side. Okay, which is the opposite of the front view. So is the plan, which has been reflected. I'm assuming that you're using it's an object that is water. It's not transparent, but is water is thick and it's not opaque. And you are using a spotlight just to directly at the line of sight, perpendicular to the plane. And that shade is projected onto the bottom, which is in this case the bottom of the box. In this case, the horizontal plane. Now, it's of utmost importance also to pay attention, especially when you are dealing with the orthographic views. Now, I want to use the 6 principles that I've just shown here. I'm assuming that now if it was a box, and take a box as it is as normal, I want you to visualize by unfolding slowly this kind of box. You've been, ladies, you've received some packages of gifts in a box, or just it's an engagement ring or something beautiful, just a gift. Let me see, for men, you bought let me say, a TV, which is a blender. Okay, in there is that kind of box that you want to open now and take on your items or your commodities from the box. Now pay attention to the unfolding of the box from the plan. We are using the 6 principles. My apology with the background. Okay, there's a Bobel. He's asking some questions. Okay, let's proceed, please. Now, it's very important. We start by unfolding by opening the top part. We assume the box is hollow. We had placed the solid object just by there and projected it. Okay, and trace the views on all 6 principles: the front, the side, the top, which is the plan, the bottom, and also the rear part. Okay, now if we start to unfold, what we're able to see will be demonstrated. That will be the same method with, very important, pay attention to this one, because we'll be using it actually in the near future when we'll be doing about solids and projection of solids, among other things, but I'll explain later. Okay, now what will you be able to see? Those are the views in the 6 planes, 6 principal planes. You see, the front view is the same as it is on the other side, only that it's, I think, the position because of the unfolding of the box. However, when we are projecting, they were facing the same direction, the same shape, only that it has been turned opposite. In the same manner of the plan, the plan remains to be the same, but if you pay attention into the edge of the lower part, now I'm talking of the 6 views that are projected after unfolding the box. Okay? Pay attention to the plan. It may seem to be the same, yes, on the circles, both plans, or the front view. Let me say the front view. On the bottom view, it was there. It's just different where the edge of the part which has been cut is placed. It's from the top. Whereas on the top view, you can see which is visible. Okay, in this case, the edge of the base from the left side is from the lower part. Okay, now I will now go straight away into the actual orthographic views in this case to be able to recommend when and how you're supposed to select the front view to give you the most descriptive features, the longest line, the longest length of the depth of the front view, among the other key recommendations or key guidance that given you in selecting the most descriptive view as the front view. Yes. Now, there's a good example. I have an isometric block which is in crane and in 3D on the upper left corner here. And there are three, and there are the multiviews benefit. Okay. Now, I have I have cancelled one of the view, which is the same as the side view. Okay. And pay attention to this. What I was just explaining. The two holes from the front view cannot be visible. They coincide with each other, and therefore the inner lines are only just 2 not 2. Therefore, we take the front view from the left side, which can give us the most descriptive features or contours, whereby we can compare that there are hidden features like the two holes, and also there's another horizontal hole that is not visible to what is not visible from the front view. Yes. Now, why have I cancelled the left view in this case? This is what makes an engineer keen. One, simply because I am viewing it from the left side. Okay, that's where I have drawn, viewing it from the left side, that's where I've selected the front view. Hence, the side view has been drawn from the right side. So, the side view has been drawn from the right side where we are viewing it. Later, I'll be able to explain that one. This is third angle projection. And when we're going to move from the first angle projection or third angle projection, one and the same apart from the plan, which interchanges. The side views are dependent on the point of view. The side view, pay attention, are dependent on the point of view. Let me proceed again. Okay, let me proceed again to the next slide. Right. Now, I have more than once again talked about lines that are usually used. And I have not once, not twice, but talked about the precedence of lines. It's very important, very, very important when drawing, especially this where beginners make mistakes. You don't get to differentiate between hidden lines, center lines, and other lines, like the phantom line, sectioning line, cutting lines, and the solid lines. Why am I talking about this? Because once you miss that one, then there is essence of engineering drawing and design is left out. Now, objects are drawn by lines, yes, but which kind of line? If it's something that is visible to you, you use a solid line, and you know the right stencil. I've talked about the right stencil. The harder the stencil, the lighter it draws. The lighter the stencil, the thick it draws, the darker. Okay, so for H is a good of what you call the stencil that has the stencil, so you can use it to draw what you call construction lines. And construction lines are just guidelines to help you before you can draw solid lines which are visible and darkened. Okay, Hidden lines are what you call dashed lines. These are used to illustrate or to show hidden features or invisible edges of specific objects. Like when we have a hole, we've just seen here in most cases. I've just used that one to illustrate. Let me just go back again quickly because it's important. As you can see in the front view, the hidden lines here. This is a very good example. There are also center lines. Okay, like in the plan, you can see there is a center line that is running from the hole throughout to the small circles which are visible from the plan. Okay, that's a huge long center line that's been drawn to combine the two because they are symmetric about a given point, both both holes. Okay, now also check on the front the side view. Also from the top, in the same manner, there is a center line that's running from the top to the bottom. In a center line is drawn differently. A long dash, short dash. Okay, a long dash, short dash, long dash, short dash, long dash. Okay, a gap. So in the hidden line, it's just a dash, dash, dash. They're even, they're distributed. I demonstrated in our previous lecture. You can just check on the sample examples of those lines. Now, uh, ladies and gentlemen, when we talk about hidden features, yes, they may be hidden from one view, but that's the principle, that's the beauty of just visualizing and also be able to navigating when you have a 3D. If you treat it at a given point, for example, a given object, then you're able again to do what? To view it, the hidden features. For example, from the side, the front view, okay, you cannot tell about the curve or the cavity or the curved edge, which is illustrated as point C. But if you're from the plan, you'll be able to see, voila, it was what? It's carved in a manner. Okay? From the front view, you'll not be able to see the hole that is visible from what? From the front side view. Yes. Either way, from the plan, you'll not be able to see the hole that is horizontally visible from the front view. That is demonstrated by using a hidden line. So this is where hidden lines are used to depict or just to show hidden features or edges. They're very important. If you miss that one, you've miscommunicated to anyone who is going to produce that kind of part, be it in any given area in biomedical, which was just a very, where precision is key. So always pay attention to each and every thing that you do, especially in orthographic views when you're drawing. Okay. Wow, beautiful. Potential or lines or touchings, which are partially drawn on what you call cylinders. Sometimes lines coincide with each other depending on the point of view. Okay? Now, let me use the 3D view that I've just of a small picture that I've just drawn here. If you view it in the front view, oh no, in the front view, yes, it's just like a window with one line which is visible in the middle, like a curve, as you can see. But when it is as it is in 3D, you'll be able to see what an edge as in the plan. You will be able to see the two edges. But from the front view, the same line is because it's on the same plane. The same plane, it means it's lying on the same surface. It's like horizontally in front of you. You're viewing it from this side, and there's the same line. Check for example paper, and assume it's an A4 paper, and put it to be or horizontal, or just lay it on your hand, and assume that you're able to do what? If you incline it at an angle this way, you'll be able to see what? Two sides, the edges, the back edge and the front edge of the line. But if you place it in a manner that your line of sight is exactly perpendicular, you'll not be able to see the what? The rear line edge or length. It's coinciding with the front one. And that's what I meant by being potential to. And therefore, if you want to pay attention, you cannot. I've noted that some students, beginners, in my early onset of teaching engineering drawing and graphics, who would separate the tangential lines at a point distance of, say, a millimeter or just 2 millimeters. It was very humorous. And they say, when I was asking, how did you come up with this? He's saying, you see the two lines here, and since they were coinciding, and now you can't draw them along one line. So in this case, I had to separate them. They were genius. They were inventing science, but they wanted to they memorized. They left out the visualization. Visualization is very key because it's a line that is perpendicular. It's like you're putting the same the same plates, or let me say the same sheets of plates, okay, which are of negligible thickness, and say they are 100, and you place them equally aligned very well on the floor, okay, and you're standing from the top, okay, you won't be able to see all the edges from the other side of you only be able to see just one block of rectangular plane as the four sets of all edges. Yes, that's the essence of visualization. Further, I want to illustrate this by I want to make a note of the following. Lines are very important. At times they can be tangential to each other, or edges or hidden features can be tangential to visible edges. For example, if you have a center, let me say you have a hidden hole which is drawn using, for example, in the orthographic views using hidden lines, and it's coinciding with an edge. Then before I'd say that a given line is given precedence over the other. So when one type of line falls in line with a different line type, you have always to call what you call, or you have to consider what you call precedence. Word ranks in this case. So, one, object lines take precedence. Object lines are the ones that are visible, or the dark lines, or the edges that are visible to you. They take precedence over what we call center lines. So, hidden lines take precedence over center lines. And no, now let's wait. We are talking about three lines here now. The visible line, object line, which is the for example visible edges. Okay, I'm calling them object lines. They're taking precedence over what we call the center lines, and center lines take precedence over hidden lines. Oh, hidden lines take precedence over center lines. So if you had a center hole, for example, this kind of curve, I would just use it to illustrate, and you want to draw, it's coinciding with another edge on top of it. So in this case, if there is no what we call, it's not visible, the line is not visible, the edge is not visible, then in this case we'll just be drawing the hidden lines. But if they are neither of the two, then this is where the center lines only can remain as a circular in nature, and the center line is drawn. So, which is the least in this case? The center line followed by hidden line followed by object line. However, we'll come later when we want to understand the internal. We've talked about isometric projection there before. It's in 3D, an example of this block. For us to understand this, for example, 3D blocks, we need to do what we call sectioning. Sectioning is the cutting. In biology, for those who used to do, is the dissecting to understand the internal features. For those who laugh, the dissection is an interesting terminology. So there's sometimes we need to section That's what the technical terminology, correct one. To understand the internal features, where they are not visible with your naked eyes, you need to do what you call sectioning, or just if it was a curve, or just like, for example, this kind of block, this one is easy because it doesn't have features which are hidden. Later, I'll just give you an illustration of that one for you understanding. So pay attention to this always. Section lines I used I used in sometimes to illustrate or to give more understanding of the internal features of a given plane. So they take precedence over what you call center lines. And there's a difference between a section line. It's almost as a center line, but it's darkened. It's almost like the temper is darkened and thick, darker and thick. The thickness, the font size. Let me use the terminology. Font size is different from the center line of the actual drawing. It's a little bit bigger. You want to increase it. Okay, I'll demonstrate later using the actual uh, demonstration of 3D, or just maybe probably in our physical classes. Okay, I have just talked about different types of planes. But remember, when something is directly in front of you, perpendicular to your line of sight, you can tell the actual length. But if it's inclined at an angle, you can't tell the true length. In this way, we always have a problem. How do we get to tell the actual length? The actual length can be determined based on what we call specific views or planes, depending on the point of view. Sometimes many beginners confused about this one. Okay, a normal plane, which is always parallel to the principal projection plane, you can only see one view as the true size or the true length. If you incline, for example, in isometric projection, this is what we are tilting at an angle. For example, here is this book. If it's directly in front of you, you can just say what, a rectangle, right? Let me say this what, portrait format, or landscape. Let me put your landscape what we use in drawing in landscape, right? But if we incline at that one, can we tell the true length when you're looking at it this way? No, the true length is distorted in this case. You can't tell it, but unless it's directly perpendicular to your line of sight. Yeah. So when they're tilted with respect to two principal projection, we see two views. Okay, and there's no true size or true length in that one. So you see it in oblique. Oh, oblique is also what another type of projection that we'll talk about later. But that's what we call an oblique plane. Is when you are inclining an angle, an object at 45 degrees with respect to all the principal projection plane. Okay, and you can be able to see the three views. Still, the three views which are visible, neither of them can be represent the true length of the object. Now, I would like to use this demonstration for you to be able to understand or get the very basic fundamentals of services. I'm still going back again to the same glass box. I've been using it entirely in our discussions, and it's very important because it will help you always to visualize. Now, we have the front view, the front of plane, the proper plane, which is as the side view, and also the horizontal plane, which is what we call the top view. Okay, in the top view, there are very basic things that you really need to pay attention to. We have marked in this for our demonstration. I've marked parts, like for example, or starting with the front. Let's start with what, the front view, whereby we have point what, point A. Okay, as you can see in the 3D, visualize in the 3D. A, the 3D object, okay, the glass box. the 3D object. I mark it as A. B is the plan, partially part of the plan. D is part of the plan option actually, which is chopped out in a little bit inclined at an angle but cut with a plane. Okay, it's like you're taking a block and taking a knife. I assume it's soft in cutting it at an inclined angle to slice away the part. And E is also is a block. Okay, is a block or like that kind of box. You're taking an edge or just a knife. Is a block, a cube, or let me say soft like this, and you are slicing it to cut two planes, which is the side view and also the front view. And we've labeled it as E. In this case, we're using them to illustrate the very basic fundamentals of visualization. Okay, now remember when you cut, for example, this edge that is perpendicular to us, I'll use later Inventor to demonstrate that for your understanding. You create another surface which is shared by two planes. Okay, in this case, the frontal plane of view, the frontal plane, and also the profile plane. Now, the question here always is, if you're able to view from the side view, what will you be able to see? Would that side be distorted? That brings a very interesting discussion. The size of the front view, the overall size remains one and the same. What changes is the visible edges that have been sliced or sectioned or cut. Okay, these edges are demonstrated in the front side, as you can see under the views, the orthographic views. On top there is the isometric drawing in glass box, and also down there are the views, the front view, the side view, and the top view. These are graphic views. Okay, pay attention. In front of you, you'll be able to see if it was the front view. As it's been inclined and cut, you'll be able to see the side A and E. If you go to the plan, you'll be able to see part P, which has been labeled as B, D, and E, which has been chopped a little bit inclined based on the colors. And from the front side view, you're able to see if it's directly perpendicular to your line of sight. You'll be able to see D partially, the one inclined, which has which is also covering the height, which is the edge view of B, and also E, which is the edge along the edge view of A, and also C. Those are the three views. So I've used this box to illustrate the 3D view surfaces, or which are symmetric, and how you can visualize when objects are what sectioned, not part of section, but a little bit what cut along the edges. These are the basic fundamentals of view surfaces. We are almost towards the end, and there is another illustration to help us further visualize and understand. Well, here in this case, I have a block. It has some more features now. In this case, it's no longer solid entirely. Yes, it's solid, but it has a hole, and this hole is along the part I've labeled as. I'm talking about the 3D view, the 3D view. Okay. How do we get to configure planes? What are some of the very basic rules that we need to apply or here and there? Now, there in the mark of the arrow shows what you call the top view. Okay, pointing directly towards 2, but it's not exactly 2 is an edge of the box. Okay, in this case, I've used edges now to illustrate. I'm gonna set up some rules in order for you to be able to configure now, like 1, 2, 3, and 4, 5, and 6. Those are some of the specific edges. Now, pay attention to this. The top view is perpendicular to the surface D, whereas the line of sight is inclined to the surface C. I repeat again, the top view is, in this case, is perpendicular to the surface. The surface is D. Okay. Now that surface we want to assume it's cutting through. Okay. Assume it's bigger than the entire box itself. Like you've taken a small box and you placed it on your floor here, which is straight and smooth. Now the surface is using D as a point of reference. Okay. Now the next one. I've said again that the line of sight is inclined to C. Good. It means what? Perpendicular to C is inclined to C. Okay. Now the front view, its line of sight. Okay. First of all, the line of sight is parallel to C. The line of sight is parallel to C. What is point C? Now it means when you're viewing it, it's not what? It's not perpendicular or inclined but parallel to that one. Okay. What you're able to see in this case, because of the colors I've shaded using different colors for you to understand this, the parts that have been cut hypothetically. Now, in this case, from the front view here, you see it's in the lower left corner is circular in nature, is a curve. Okay, an arc is used for that one to draw the outline. Okay. And then you just go to point what? The corner is 1, 2. The edge 1, 2 is coinciding. Remember when we were talking about tangential lines? Now these are tangential corners. Now 1, 2, 6, 3. Marking where I've just marked 6, 3 is a point which is coinciding, because when you're viewing it in front of you, you'll not be able to see 3, but you'll be able to see corner 6. The length 1, 6 is visible. It's the same as what? 2, 3 if it was from behind the view. Okay. And also check on where in the front view. 5, 4. 5 is in front of you, but 4 is tangential to 5 at a point when it's in when viewing from the front when it's perpendicular or viewing from the front side. Okay. And also D is not visible. Pay attention. From the 3D view, G or the section of the surface G is not visible. Cannot be visible from the front view because you're viewing it perpendicularly, and therefore it's not possible to see it. Okay? But D, yes, can be seen slightly. But you can't see as well C, because you can only see surface C from the front side. So in the same manner, I have illustrated in the right side and also from the plan. In the plan, you can see surface A. Surface A is visible, and surface D is visible, and also partially B is visible, and as well as C is visible. But there's something you need to understand, that you can see G totally again. In this case, from sorry, yeah, in the plan you can only see surface G. You can only see surface G from the front or from the right side. Those are the very basic rules of configuring planes. Based on that rule, it's important, and again, of utmost important, to always label. These are most of the challenges that students face, especially when we be doing projection of solids, etc., etc. You've got to understand that labeling is very important, because it gives you a clear understanding and not confuse the sides that coincide with each other. Okay? A section of solids and also other services. When we come later, you just be able to understand into details how we do that one. Now, I'm gonna use this illustration for your understanding why labeling is important. Now, the 3D view is very easy. It has been drawn as such, and you're able to see it. what you see basically very important are the services. Like 2 is a service, an entire service, 7, 5, 6, 3, 1, 8, and 9, and 7. So there are up to 9 services that are visible as, and also yes, there's a hole there that is labeled. So as for what I want to say is very simple. They are, depending on the point of view, there are services that you cannot see, and those are what you call the hidden features or hidden services. But when you tilt or just move to another perspective or from a different angle or view, you are able to see those hidden features. So that's why we use what you call orthographic views or multi-views to be able to communicate concisely and precisely the details of a given isometric drawing. Finally, as I said again, labeling is key and important. Now, pay attention to our labeling there. Uh, uh, Labeling helps us to just visualize an object. Example, this is a very simple, this diagram, we've just drawn it in our Inventor, and we have it. I'll just open it later and use it to illustrate. But again, in the front view, let's click on the angles that I've labeled here. Oh, I'm labeling the edges now, points now, like 1, 2, 3, and 4. Is from the side, the side view, the right side view, and then we go to 5, 6, 7, 8, 9, 10 from the rear, and we come to 11, 12, and 13. That's the end of it. And also, do we have another? Yes, the up to 13 and 14 also. Yes, there's 14. Yeah, which is the lower corner, which is not visible to us, the edge that is not visible to us, but it's been drawn there by projecting from point what? The axis from point 8 downwards, and also to point 2, it's meeting at point 14, and also from 13, which is the bottom. Yes, the bottom surface, the horizontal plane. Okay, which is in contact with the horizontal plane, the surface. Now, as you can see, that is the best method of labeling, whereby you're able to visualize and understand points that are coinciding with each other, or lines which are tangential to each other. And that gives you an understanding of what. This kind of one more thing. If I'm using this kind of number, it tells you that the edges, for example, 700. Let's start from the front view. We are talking of 13 and 14. 13 and 14 tells you there's another edge behind that one. So it means it's not just it's in 2D, but yes, it's communicating that you are communicating that there is another length which is coinciding with 13, which makes it what? Not just a 2D plane, but more of a 3D object in that case. If you just go, where is this kind of 14 that we are talking about? 14 is shown then where? On the top view, and as well as on the right side view. And now, once you communicate that one, we are able to understand the length, the depth. It tells you that from 13 to 14 in this case is what length it can be measured. It can be counted for length, etc. So labeling is important to help you visualize and give an object, whether it's just some hidden features at the length, and the sizes that can be visible and hidden as well, depending on the point of view. We are coming to almost an end of this, and well, I'm gonna use AutoCAD, not really AutoCAD, but for you as beginners, I would urge you to also learn AutoCAD. It's a software program for design by Autodesk, and also you can use other software program like Inventor, among others. There are quite a number of what works for you. For me, what works for me, I use quite a multiple number of programs in designing. So you start from basics, especially AutoCAD, will be able to learn a lot in drafting using the software. And in most, Orthographic views in such a case, when you're using AutoCAD, it is able to give you what you call, you use layers to manage and create some lines, because you select the thickness of the line, what we call the font size, the type of the line, hidden lines, and you can freeze the layers, and freeze the layers you want to see what you want to see. And this is what I want to say. Why AutoCAD is very important. I've used this illustration of AutoCAD for your understanding. You can, for example, be an electrical engineer. And on working on a project like requires, for example, an architectural drawing would require a structural engineer, an electrical engineer, a civil engineer, mechanical engineer for plumbing and features, etc. All of those are all of those specializations are different, but when they come together, they combine. An architect cannot just do, for example, cannot do what you call electrical kind of things, because they do not understand. They may have a concept, yes, but they may not be able to be precise as electrical engineers to be able to understand the principles of doing, for example, electrical installation in a given building, or not literally electrical installation, but talk of other features. Let me see, CCTV installation, water features, etc., etc., and other security features, etc. But would require electrical installation and also design. So what we do, or just this what we call cohesion across, or synergy across these fields, whereby upon completion, the actor can freeze his own kind of layers he has used, which are dimensions and others, and can give the overview or the entire plan to an electrical engineer, who will study the plan and also do the necessary in terms of laying out the electrical infrastructure, or design within the drawing. And also the same way, upon completion, those layers can be frozen, so that you don't have so very many lines drawn, because it's the same length. It's the same way you are going to place a window, just a circuit, or just let me say a sailing light, or just a switch, or just a socket. And here it's falling on a given length, so you've got to understand the length. You cannot be drawing several of them and showing dimensions, dimension of a circuit, dimensions of a window, dimension of a roof, etc. So they are frozen. They are frozen. Layers can be frozen. So at least you can all see what you call what you want to see. And say electrical lines, etc., etc., etc. Hypothetically. Now, so layers I used in the AutoCAD. It can help you to draw object lines, hidden lines, sectioning lines, text line and dimension, titles, or let me say titles, yeah, in text, etc., etc. So it's very useful, and you'll be able to either draw using what you call third angle projection or first angle projection, as you may want to use it. Okay, and that brings us to an end of our demonstration here right now. And later on, we'll just do what we call projection, orthographic projection of lines. Pay attention to this, because it's very important. We've just talked about an overview. But again, you've just seen I have done an orthographic views, but which have just been labeled points which are coinciding with each other, and lines which are tangential to one another previously. So later, we'll just do what we call orthographic projection of point, lines, and surfaces. It's very important for us to understand the true length, how we can define that in our actual practical license when we're gonna do them. So that will help us to understand so many things. So later in our study, we will do that. So to give you just a tip of what I'm talking about, this is what we're gonna do in our study. In the next lesson, we'll just be doing what we call orthographic projection of points, lines, planes, and solids. It's very important before we proceed to actual drafting or actual practical license. And thank you for your time. And I would like to hear from you. For those who've subscribed, thank you so very much. I give thumbs up to our lessons. And for those who have not subscribed, please do subscribe to our lecture notes, to our channel. Apology for that. And also drop in some comments light up this room with some questions that can help us to understand what you are lacking, or what you want to be addressed next, or what you want to be helped with. And also raise up some questions. It's very important, because these questions are equally important to us to understand where you belong. And thank you so very much. Until next time, see you. Yes.